Okay. So today, as I said, is going to be one of those very important lectures. Just to motivate you, I think I can wave my hands a whole lot of times, and I did it the whole semester to telling you how it's important for the industry, how the topic is important for robotics, etc. I mean, all of this is true. I'm just not going to do it this time. Instead, I will tell you that this particular topic has led to previous year students, first of all, to excel at the exams. One of the best performances that we have seen during the exams were people who understood this topic. Probably tells you more about exams than about the students, but anyway, this topic was made a huge difference for exam performance for some of the students. I mean, hopefully that doesn't sound very, very important to you. My exam performance is just whatever. Hello, hello, hello. Instead, I'm going to tell you this topic has led some of my students who followed up, in research to produce very valuable research output. The research output for one of my students who still works with me, directly after finishing this course. So this course, he finished it last December, right? Or wait, I believe last November, it was the first block. So already in around December, January, we were able to produce state-of-the-art result that was more or less equivalent to what people published in a Q1 paper. I mean, that's scientific lingo, but basically in a paper in a reputed journal. So, it's like not bad for a master student, right? And you can imagine, like, you know yourself, that was a guy who was, just a few weeks ahead of you in terms of what you know now. So you can, that's maybe can tell you something about this topic. It's just the opener for a lot of possible, possibilities in research. And then just a few months later, he actually made the work that became a contribution to the state-of-the-art. So, he was first able to successfully reproduce the state-of-the-art results from a very good research team. And then he contributed himself. So, like, less than a semester after finishing this course, based on this particular topic, like this topic is 100% what he used for his research. And he also had one lecture, exactly like what you're going to have. He managed to contribute to the state-of-the-art. That tells you something about probably state-of-the-art rather than about the topic. I mean, currently, this style of writing optimization problems has not yet perforated, spread as much as other topics did. So, in a sense, it is kind of like an opened window opportunity for you to do research, mostly because a lot of researchers who solve very hard problems don't use this type of tools because those tools are recent. So that is the story here. I don't want to say that this topic is somehow like magic or whatever. It's just a new tool, and you can take advantage of its newness to use it for your non-styled applications. And the key to success here, I mean, if we just define success as being able to contribute to the state-of-the-art, is just to find a field where people solve important hard problems, but don't know yet about the effective tools to solve those hard problems, which happen to be developed in a different field. And it's like, it sounds like cheating, but that is pretty much what science is, right? You invent a tool for one application, and suddenly you can solve 10 other problems in different applications, and that is a valuable contribution of a scientist. So, it's like I urge you to try to get what I'm saying here in this topic, and then try to think on your own about what you can do with it. All right, we'll go back to the motivations later, but let's just jump into what we're talking about. Mixed integer convex programming. All right, let me just show you what mixed integer convex programming is. Well, this expression number one is a linear program, except there is one difference there. What's the difference? By the way, let me just see if we can use camera slightly more effectively than I usually do. So, we'll see if it is helpful or not. All right, so here you can see we have one new different element. Everything else is kind of the same, but we have this strange constraint in the bottom. I mean, strangeness maybe comes in the fact that we have like x and y, but it's, you can define z, which is equal to x stacked with y, and it would be the same thing, right? The only strange thing here really is this constraint in the bottom, y equals to n to the power of n. What is this n, big N? Well, it's integer numbers, integers. If you see the script, where you have those, parallel lines, it usually refers to some sort of numbering system. You're familiar with it, right? Let me demonstrate on the blackboard. Maybe this camera, jumping is not the best idea after all. All right. Let me put the camera back on. So, like real numbers are often depicted like this, right? Rational numbers sometimes are depicted like this. Integer numbers are sometimes, often depicted like this. Binaries are often depicted like this. Complex numbers are often depicted like this. That is a typical scientific notation. Typical, not, not regulated to anything, just typical, okay? So, you can use something else, but this typeface usually is reserved for numbers. Sometimes for polynomials, like this. I wouldn't be surprised if you find this as a description of polynomials, for example. But typical reals, integers, binaries, complex numbers. All right. So expression number one is expression for mixed integer optimization. So the only difference between this and standard convex optimization is that some of the variables are restricted to be integers. So where x can be whatever, 1.2, 1.7, 3.12, etc. Y has to be either 1 or 2 or 3 or 0 or -7. Cannot be a fraction. Okay. Yep. That is the story. So sounds good, right? I mean, is okay. Why not? The only problem is that it's not really convex, right? Why? Well, we know that convex domain is a domain where any 2 points can be joined by a line, and the line has to lie inside the domain. Well, let's say that this dimension is x. Let me make sure that people can see. Let me put the camera a little better. Okay, so this is convex domain. So let's imagine that this dimension is x and this dimension is y. Well, let's say x allows us this interval. Let's say y allows us this interval. Okay, how does the domain look? Well, y is integer. So it can only assume those values, those discrete values. Okay, so here, from here to here, we are allowed to have anything we want. From here to here, oh, sorry, yeah, horizontal, right? Yep, true. So from here to here, we are allowed to have anything we want. From here to here as well. Same here, same here, same here, same here. So this is our domain. Almost definitely a point here and point here are not going to be joined by a line that lies inside the domain. In fact, it's going to intersect domain in the finite number of points. So this doesn't really work. It's not a convex optimization. But we'll still call it convex, and we'll come back to it in a second. But I just want to point out what's the strange, difficult thing about it is here. Right, we can do the same thing, but with a quadratic cost. Notice expression number 2 The only difference is the cost function. And you can, mix your integer variables together with your non-integer variables in this fashion. And notice I use the word mix, and that is kind of like where we get this mixed integer optimization, right? We just use them together. Okay. So far, quite obvious, right? Now let's just dwell a little bit on the, on what's going on here. Well, first of all, mixed integer programs, as I said, are not convex. The word convex is referring to the fact that if you allow this variable to be real instead, the domain would become convex and the cost function will become convex. That is what it refers to. It refers to the fact that you could have made it into a convex program. The only difference between it being convex or not convex is the fact that your variables are integers. And that is a big difference. But algorithmically, there is advantages that you can take out from using convex domain and convex cost function, but integer variables. There is a way to solve it efficiently. And that is why, and using convex optimization, that is why this program kind of belongs to convex optimization framework, if you wish. Okay, so mixed integer programs are usually solved using branch and bound algorithms. What's the branch and bound algorithm? Well, if we're not going to study it, and we're not going to implement our own algorithms here, same as we didn't for interior point methods and other underlying convex optimization algorithms. But what it is actually very simple. Imagine you have your integer variables y1 and y2. So your mixed integer variables, let's say, currently assumes value 1 and 2. So what you can do is, for example, test, and the gradient points in the direction, let's say this is the value, and this is the gradient. Gradient points in the direction, let's say, 0 and 1. What does it mean? Well, it means that I don't want to be caught up in the science, so don't take it too seriously what I'm saying. But it means that the function decreases in the direction 0, 1. Okay. Maybe it increases in this direction, then you would have to put minus sign here, but whatever. So you have gradient that points in the direction 0, 1. So your next guess, this is your current guess, your next guess can be, how about we take v equal to 1 and 3? Or maybe 1 and 4. Why not? Right? That's where the gradient points. So how about we take those values? And maybe gradient would point in a different direction, right? Maybe something like this. The gradient, sure, you can restrict it to integers, it doesn't matter. Gradient is just direction, it's not a length, doesn't matter. Okay. And maybe here it points to something like this. I don't know. Sure, good. Why branch and bound then? Well, because that cost function here, let's say cost function here was 3.37. And there maybe cost function is 3.65. Oh, sorry, it should decrease, right? Is 0.5. And maybe here cost function is 2.99. And then you can kind of like see this tree of, that you grew. Like from this, you got those two guesses. And this guess is so far better. So maybe you would go from this guess somewhere else. So this is kind of like the story. But how do you get those guesses? Well, first of all, you fix those variables. And then you solve your QP, like this QP, for example, with those values as constants. That you can do using interior point method, right? That's how you evaluate your cost, right? That's how you evaluate your cost. how do you find gradients? Well, to find gradients, what you actually do is you relax them. And instead of fixing them, you relax them. You say, let's allow them to be integers, reals. And then you solve a different QP where you have real numbers there. And you can find that what I'm saying here is actually I just hope it is not completely incorrect. So I don't won't want to mislead you, but that is pretty much how close enough to how it's supposed to work. You replace them with real numbers, and then you solve your problem with them as reals, and you get a you get the idea in which direction your function decreases, and start from there. Okay. All right. So branching bound algorithm in worst case scenario. So the idea of branching again refers just to integer variables. They have a number of values and so on. By the way, one last thing. Maybe I shouldn't spend so much time on this topic, but why it's called branching bound, it doesn't matter. But I think there is just one last thing that you can use from a piece of information. Imagine that. Okay, we'll go to it back just in 1 second. Last point, let me make it here, and I will go back. So in robotics application, sometimes instead of integer variables, we use binary variables. So sometimes y is not integer, y is binary. So it's either 0 or 1. That doesn't make it any more difficult, right? So, clear enough. We just use binaries. We still call it mixed integer, but sometimes we say binary constraints, stuff like this. All right, now let's imagine that y1, y2, y3, y4 are all binaries. Then what is let's say your initial guess is something like this. This is the value of your binary variables. Now, here you can kind of see why you would call it branching bound. You can say, okay, what if we change this variable? We can have 0, 0, 1, 1. And here, what about if we change this this variable? We have, this. And you can evaluate your cost at each of those branches. And you can kind of try to follow where the cost decreases. So with binaries, it's kind of obvious that if you change only one variable, you kind of branch out. Again, don't want you to get caught up with those notions. And you can study branching bound algorithm on your own. They are not extremely mature yet, and but the underlying algorithm is very simple. But maturity is not, probably is not reached yet in the field. What I mean maturity? Well, I mean software that supports it is still being developed. For example, you can find branching bound algorithms for QPs very easily. If you install CVX, you'll probably have one of the solvers supporting branching bound algorithms. On the other hand, it's going to support QPs, but not going to support SOCPs. So branching bound for SOCPs, you remember what SOCP is, right? Second order cone programming. It's not going to be supported by default. You'll have to use Gurobi, for example. Gurobi is a commercial solver, so you would have some difficulties with that. Why am I pointing this out? Oh, just to say that one day we will definitely have a default, easy, free solver, mathematical library or whatever that would do all of this, but not now, not yet. So far, you need to either use commercial solver or still it doesn't perform super fast. Maybe eventually they'll perform faster, etc., etc. There are issues. What I'm saying, and branching bound algorithm is a family of algorithms. Obviously, the implementation in Gurobi would be different from implementation in other softwares. So be aware of it. All right, good. Now, let us consider, so before we go to examples, this is an example. Let me ask you if you have questions. Yep.
Why is it useful to use mixed integer programming?
Oh, sometimes, and I'm going to give you a very good example here, but sometimes your variables are simply integers. Like you cannot have a non-integer variable. And in this case, you'll have to use a mixed integer optimization. Let me give you economic examples, because here I'm going to give you robotics examples, but let me give you economic examples. Let's say you're talking about how many pieces of equipment you want to buy. Let's say for your factory can install robots. You can install 5 robots, 6 robots, 7 robots. Each one of them will increase throughput of your assembly line by, fixed number of units per day. Each of them has a cost. And you have a constraint on how many throughput you can maximum organize, in the best case scenario, because you're constrained by materials that your factory gets. Let's just say you assemble like, electric cars. You're constrained by the number of batteries you have. You cannot assemble more than a fixed amount for electric cars a day. On the other hand, your assembly line currently assembles way less than that because it is constrained by how many robots can do welding. So you want to maximize your best, make the best investment. Also, you can say that maybe maybe this investment can be done not in the robots, but in building a new assembly line operated by humans. And you can say, okay, we can assembly line. You cannot build half assembly line. You can only build them in integer quantities, right? You can build assembly line. It costs the same as, let's say assembly line costs, I don't know, $200,000. And one robot costs, let's say, $110,000. So it's not one-to-one. You cannot exchange 2 robots for one assembly line. You can exchange 3 robots for one assembly line, but that's, you'll have extra cash in the bank. An assembly line operated by humans can have this much throughput. An assembly line operated by robots, this much throughput per robot, and etc. So, and also you want to compute the cost of operation over the next 12 months. So you know operation cost of a human per month, and you will know operation cost of a robot per month. And basically now you want to variety optimization problem, like what is the best to buy? How many robots, how many assembly lines, in terms of cost, in terms of throughput. You can also convert your throughput into money. You can say each unit of throughput is so many dollars. So what is the best economic decision for the next 12-year horizon? So this is a mixed integer problem. You cannot solve it as a convex optimization because the answer will be 2.5 robots and 1.3 assembly lines. And it's just not correct. And you cannot round it off. You cannot say 2.5 robots is 3 robots and 1.3 assembly lines and is one assembly line, because quite possibly that's not going to be optimal. Okay, so that is a very economic example. Economy actually, I will take your question in a second. Economy is actually where those types of problems have been developed. And there is an entire field. So we're studying here convex optimization, right? And maybe I gave you incorrect impression that this is the same as optimization in general. Hopefully not. Hopefully you remember like nonlinear optimization. So gradient descent, all kinds of stuff that they do in machine learning, etc. But those are not two only fields in optimization. There is another one. It's called, we can call it discrete optimization if you want. I think there is even a better way, better name. It slips my mind right now. But anyway, discrete optimization, if you wish. And that is mixed integer, just mixed integer. For example, maybe you heard about knapsack packing problem, where you have a backpack with a given volume. I mean, mathematicians, they have, very different ideas of what a backpack, looks like compared to normal humans. But let's say this is your backpack, and here are your items, and etc. You have items with different shapes, and you want to find how you can pack them into this backpack. You want to maximum, each item has utility. Let's say this item has utility 7, this 1.5, this 0.1, and you want to pack items into backpack, and maybe they have like quantity associated with them, etc. This is a packing problem, and is obviously something similar to mixed integer. You would have to find the place of them, and you would have to find unique position for each unique item. And by the way, this is often solved using mixed integer. However, there are even better algorithms that those people develop. So here we touch a different field of optimization, discrete optimization. All right, your question.
Yes. So branching bound method is example of mixed integer problem.
Branching bound is a solver that is going to solve your mixed integer problem.
And then what is the state-of-the-art solution in mixed integer?
What do you mean state-of-the-art solution?
You said that your student previous year reached state-of-the-art.
No, what I said was using this material that you're going to get through this lecture, he managed to solve a particular problem related to tensegrity structures, automatic generation of them, etc. And his results are slightly improving the best that we found in scientific literature, in small ways and in very specific circumstances, but they are improving on state of the art. And that is, and his learning was based on this one lecture. Well, that's what I meant. He did not improve branching bound or anything related to optimization itself. He used optimization to solve applied problem in his thesis. So, okay, more questions? No? Okay. Let's consider FOOTSTEP lying problem. So here is a problem. You have n convex regions described as inequalities, so H polytope representation. You remember already what this is, right? H polytopes are, no, I cannot write it. Let me erase. So you have H polytopes. 1, 2, let's say 3. Each of them represented as such. So we have H polytopes. N of them, I'm just drawing 3. And you want to find a sequence of points, we'll call it footsteps, that should lie inside one of the polytopes and lead you from start to finish. So let's say start point is here. Let's say goal point is here. You need to take footsteps. For example, like footstep, footstep. I don't know, let me just draw them a little bit closer so we can believably think that it is a robot walking. Maybe like this. Okay, so footstep, footstep. I don't know. Let me even draw another polytope here. Footstep, 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 footstep. You understand, right? The robot walks kind of like this. Okay. imagine that we have a rubble on the floor, all kinds of like stones or whatever. You cannot step on them. And this sequence of footsteps will, it only uses the patches on the floor, which doesn't have any boulders or anything else unsafe to step on. You just identify that this looks like something you step on. This is something like you can step on, etc., etc. And you plan your footsteps on those. Any questions? Okay. Now, I can formulate this as expression 3. So in expression 3, notice we minimize the distance between the first footstep and the start, the last one and the goal. And you say that any, is it correct? Let me just say. There should exist, okay, there should exist A and B in the set of all, polytopes, such that A, X less than or equal to B. So X should be inside at least one of the polytopes. We don't say it should be inside a particular polytop. We say it should be inside at least one of them. That's a big difference, right? For example, because this solution is not inside this polytop or this polytop or this polytop. It just happens to be inside this polytop. Big difference. All right, let me check the chat. By the way, guys, who are online, you can unmute and talk. Today we seem to have no audio problems. So if you have questions, unmute and ask, okay? We'll hear you probably loud and clear. Okay. So expression number 3. Is it convex? Is it convex? Just try it.
This is not a score.
Why? You can see it down the slides. That's too bad. But why? Why would you guess it is not convex?
I think because of that condition. Like one of the polytopes, not inside the polytop that I'm in.
But prove to me that it is not convex.
Maybe because you can draw 2 points and connect them with each other, and the line will be outside of all polytops.
Yep, but yeah, that's almost correct. Let me just polish it a little bit. So you can say that step number 5, this particular step, can be here or it can be here. No one stops us from putting it in any of the polytopes. But the line that connects those possible positions of one particular step number 5 is outside of domain. So this is the issue. Because here's a different proposition. Let's say you have 2 domains and you have footstep plan where footsteps number 1, 2, 3 should be inside this one. And 4, 5, 6 inside this one. Well, thing is, this is a convex problem because those can, domain of those points is convex and domain of those points is convex, and they cannot, there is no line outside of the domain. But this is not convex. It looks the same, but it's not. It's not just about geometry of a particular solution. This is just a particular solution that I drew here. Problem is that you want to make sure that domain is non-convex or convex. And here, domain is, let's say it is a flat problem, so 2-dimensional. And I drew how many steps? 1, 2, let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. 14 steps. How many decision variables do we have?
X and Y.
Yeah, 14 steps, X and Y is how many? No, polytope is not decision variable. Decision variable is what you can change. So how many? 28. Yeah, because each of them can change independently. So 28 decision variable. So thinking about a domain in 28-dimensional space would be slightly challenging. Okay, but you don't have to. You can project it always on a 2-dimensional space. You just think about this one point, project its domain on the 2-dimensional space, and that is the picture that I drew. Clearly not convex. Take this point, project its domain on the 2-dimensional space. Again, the same picture that I drew. Again, non-convex. That's how you can do it. You don't have to consider the whole 24-dimensional or 28-dimensional space. That is not productive, right? Just consider projections. Okay? Yes? What I mean is your decision variables are x1, y1, x2, y2, x3, y3, etc. up to x, 28, y28. So very big space. Project it into this space. So just get rid of all of those decision variables. Forget them. What would it mean? It would mean that you have only this point to consider. Other points are fixed. What is the domain of this one point? Well, this union of those guys, right? That's the domain. You can do the same for this combination, and domain will be the same, right? That is what I mean. Good? Questions? Yes. About the cost, yes. So with the first component of the cost here is saying that let's try to make sure point 1 is as close to the starting point as it can be. And if it is away from the starting point, we will punish it. And a second component of the cost says, let's say that the last step should be as close to the goal point as it can be. And if it's not close, we will punish it. And that is, that is the cost. Does it make sense? So other points in this formulation, which is not perfect, by the way, they are free. They can be anywhere. So for example, you can do this way. Let's say this is a start, this is a goal. You could do it this way. Starting point, then all the points are here, and then the last point is here. That is a valid solution. It's complete garbage in terms of a FOOTSTEP lining, but it's a valid solution. You could also add a constraint saying, let's say that xi minus xi plus 1 should be less than or equal to 0.5, for example. You could add this constraint saying that you should not have a distance between your points exceed half a meter. What would be this constraint? Do you recognize it? Yeah, no, I mean the name in terms of optimization problems. It's not linear, right? Because there is a norm. Yes, OCP. It's a second order constraint. So this is a conic constraint. We could add it. And then this is not going to be a QP. I mean, right now it's nothing. It's non-linear. But instead of hoping to become a QP, this cost function, because it looks like a QP cost function, instead it's going to become a SOCP with this constraint. But you can add it. And then this scenario is going to be impossible. Okay? We will see a different way to do it. Yes? So far, there are no integer variables here. All The number of footsteps. Oh. Yeah, we don't. This program doesn't do anything about the length of the footstep, so it allows this situation. We'll talk about it at the end, but yeah, so far it allows it, and no integer variables here. Notice. So, okay, but it's not convex, so we cannot solve it. We can, there are no instruments that we learned that can solve it. You can do gradient descent if you want, but good luck. Gradient descent is not going to do a good job here. Why? Well, initial guess will be, let's say, this, right? So all the variables will be here. Then it will try to push the variables in this direction. And then it's not going to be able to do anything because it has to either jump here or jump here. And that is not what gradient descent is good at. So you understand me, right? So that is, you achieve a local minima, is what I expect, with a very small gradient descent. Of course, you could cheat it. How can you cheat it? For example, you can start with a random distribution of initial points, right? But then your footstep planning may be pretty crazy. Also, what is another possibility? Well, you can, instead of doing gradient descent, you can do random search. That's going to achieve the optimal solution, but how many iterations are going to take? Yeah, it's like billions, quite possibly. All right, good. Now let's see how we can turn it into a very simple program that we can solve using our tools. Well, we need to learn something that is called Bic-M. Let me minimize the screen a little bit. Bic-M method. Bic-M is at the core of usefulness of mixed integer programs for quite a few robotics applications. Not for all of them, but for quite a few. Bic-M is a key idea that you need to understand. Let me stress it a little bit more. Branch and bound, you don't have to understand it. You can use it. Download YALMIP, it comes with branch and bound algorithm. Download CVX comes with branch and bound algorithm. Your Collab notebook will have a branch and bound solver pre-installed. So you don't need to implement it, it's already there. Bic-M is not pre-installed or anything because it cannot be. Bic-M is a way to write your program in such a way that to take advantage of mixed integer. So it's up to you. Either you understand and use it, or you don't understand and you cannot use it. So this is why it is critical to understand this piece of, basically expression number 4. If you understand what it does, you are more or less done with this lecture, and you can start using mixed integer. So pick attention here. Okay. Assume you have two inequalities. Let me highlight it here. This inequality and this inequality. Okay. And you are happy if at least one of them holds. So let me just write it here on the blackboard. Sorry for destroying all our beautiful polytopes. So what does it mean? Well, in the simplest case, it can mean, let's say, x times, let's say, okay, either x is less than or equal to 2, or x is bigger or equal to 5. Two very simple inequalities. You are happy if at least one of them holds. They cannot hold both, right? But at least one of them should hold. Okay. All right. How can you rewrite it? Well, first of all, what you can do is, let me rewrite this in terms of typical notation, which is minus x less than or equal to minus 5, right? That's the same. So if x is equal to 100, minus x is going to be minus 100, definitely less than minus 5, right? And if x is equal to 100, it's definitely bigger than 5. So, okay, makes sense, right? Sanity check. Good. Now, we'll introduce two binary variables here, C1 and C2. Introduce C1 and C2, which are binaries. So they can be either 1 or 0. Okay, binaries. Okay, now what we can do is we can relax our constraints. In which way? Well, let us rewrite the constraints here. Let me try a new marker just to make sure it's visible. Oh, 1 second. I will find one day a good mark. I don't have one. Oh, I think this one is decent. Yep. Cool. Okay. So we can relax those by adding here a huge number. Let's say m is equal to 1,000. I mean, that's not a great choice necessarily, but just let's just say 1,000. So we can relax constraints in this way. 1,000. Now both of them are satisfied for, let's say x is in general somewhere between like -10 and 10. Like x is not like domain for x is pretty small. Okay, then this is always satisfied. Both of them are satisfied, right? Correct? All right. So what we want to do is we want to switch them off and on, those m variables. So we'll multiply it by C1 and C2. Now, if C1 is equal to 1, this constraint will always hold. So basically, it's going to be switched off when C1 is equal to 1. When C2 is equal to 1, this constraint is going to be switched off. So if both of them are equal to 1, all constraints are switched off. But we don't want that. We don't want both constraints to be switched off. We want only one constraint to be switched off. Okay? How do we do it? Well, we can say that C1 plus C2 should be less than or equal to 1. So they cannot both be 1, right? Now, that would be, easy enough. But there is one other thing. You can say, so you can say here that, this is good. But then both of them could be satisfied simultaneously. So you could find a solution where both of them are satisfied. And that sounds good, right? So you would say, okay, like good solution, both of those constraints satisfy. Not for this example. This example is impossible to satisfy both of them. But for some other example, maybe it could be possible. Well, it's good if you care about this scenario in particular, if you're particularly fond of satisfying both constraints. But if you don't, if you're completely indifferent, whether or not you satisfy just one or just the other, and satisfying both has no value to you. I mean, it's not bad, but it's not good. It's nothing. Then you can replace this one with C1 plus C2 equal to 1. Why would you want that? Well, let's say you have a C appearing in your cost function. Then basically what you care about is which one of them is 0, okay? So what you really care about is who out of those two is 0. That would mean which of your constraints is satisfied. If they're both 0, your cost function can be screwed up. you can design it to take into account which specific constraint is satisfied and do something about it. And if both of them are satisfied, maybe your cost function is not going to perform the way you want. For example, if you put a, let's say your cost function looks like this. Then satisfying both of them at the same time would definitely minimize your cost, right? But maybe, but if it doesn't provide any value to you, there is no reason to do it, right? Imagine you have a area here, and somehow you, this is area where C1 equal to 0, here C2 equal to 0, and here both of them equal to 0. Well, if this is your cost function, it's going to always pick this area, but that's not the behavior that you want. You just want some priority to this area, for example. You don't want priority to this area. So this is why typically we do this kind of thing. I mean, there's no rules. It's just typically, Okay. All right, good. Now, that is...
excuse me, Professor?
Yes.
For the second inequality, is it plus M or minus M?
Here?
Yeah, the second one.
Both are plus.
Haven't we made an intersection between the solutions in this case?
So, okay.
When
the big M in this case is a good question. Okay, big M in this case is serving the role of making sure this constraint always holds when C2 is equal to 1. Okay. Let's say if C2 equals to 1, it becomes minus X less than or equal to minus 5 plus 1000, which is, minus X on this interval is going to be at most 10, right? At most 10. So 10 is still less or equal than 995, right? So on this interval, as long as C2 is equal to 1, this constraint is always satisfied. And that's the story. Did I answer the question?
Yeah, thank you.
No, thank you for the question. That is the heart of the situation here, understanding why M comes with a plus sign, etc. Okay. Good. Now, that's pretty much it, right? That's pretty much it for Bic-M method. Any other questions? We're going to go back to the example, but let's first.
So M is a decision variable for the... M is a decision variable for the...
No, M is a constant.
So I specify it or the program specifies it?
You specify it.
How can I choose the value of it?
M should be chosen to be so big that this constraint is always satisfied if C is equal to 1. But as small as possible. So in this case, I believe 15 would have been enough. That's what you should have chosen. The smaller M is, the easier it is for the solver to find gradients. So choosing huge M, like million, is going to destroy your solver's efficiency. Choosing small M is going to help. But you don't have to sweat it too much on the design stage. When you design your algorithm, you can find typical values your inequalities take, and then just cap it with M. Okay? More questions? No? No more questions? Okay, so again, this is the heart of the story. let's apply it. So let's say we have three systems of inequalities: A1, A2, A3, as on the slides. Okay, so it's our three polytopes, and we are happy if at least one of them holds. We do it exactly the same way, except you know, M is supposed to be like a vector times 1, right? It's you know, here it was for scalar case. Now we have a vector case. So in order to make a inequality of this type hold, we need to add M, but M should be multiplied by a vector of ones. Right? Why? Well, because it is n equations here. So that's why. Dimensions should agree, basically. All right. Now, we do it in a typical way. Typical way is we write our relaxation typical way, which is 1 minus C1. Instead of C1, we write 1 minus C1. There is a good reason why. I didn't do it first because I didn't want this minus to be hindrance for understanding, but that is a typical way. This on the blackboard is a typical way. Okay, why? Well, let me write 3 of them. Okay. Now, when is the first equality going to be switched off? When I say switched off, I mean always satisfied because of the big M.
When C1 is 0.
When C1 is 0, yes. So C1 is 0 means that this equality is switched off. Here C2 is 0, right? Here when C3 is 0. What we want is to have only one equality switched on, right? We don't want two equalities switched on. We want one. At least one is good, but we will just ask for one. That means that C1 plus C2 plus C3 should be equal to 1. So at least one of them should be non-zero. That is the reason for this convention, because it doesn't matter how many of them you have, it's always going to be like this. If you used C here, you would have to have written something like it should be equal to n minus 1, where n would be the number of inequalities. That's a mess. I mean, it's not really a big mess, but that's how we write it. And that's it. Notice that no, it's pretty simple. There's nothing too scary here. By the way, it was a question about M being decision variable. If M was a decision variable, it would have been multiplied by C. So you would have had a variable here multiplied by a variable here. And in inequality constraints, it would lead to a what they call quadratic constraint, right? So it's not ideal. That's the first. Second, of course, you know, I mean, not of course, but there is actually a way to make linear constraints out of a multiplication of a binary variable times a real variable. You can turn it into a non-quadratic constraint, into a linear one. But there is no reason to. Like M is a hyperparameter, what we call it. So you tune it before you solve the problem. Same as cost coefficients in your function. Okay, sounds good. Now let's go back to footstep planning. So one last one. No, okay, let's go to, let's see what this stuff does in action. So I have two regions. Let me rewrite it like this. we have two regions, okay, this situation. One is blue region, one is green region. So far, so good, right? The union is not convex. So what I want is to relax one of them with a Bic-M relaxation, at least one, right? So I would add the Bic-M like this here, to one and then to the other. Here you can see the result. So green region was relaxed, and you see the big shape. That is a green region after you added M to it. You see that the geometry of the region remains exactly the same, right? But now intersection of relaxed V2 and V1 is what? It is convex, but also what is V1? Yes. So the intersection between relaxed V2 and V1 is V1. So V1 became our new domain. That's exactly what we wanted. Now on the right, blue region was relaxed. Again, shape remained the same, only size increased. And what else happened? Well, now intersection between relaxed V1 and V2 is V2. Yeah. So you can see that what Bic-M relaxation does, it allows you to choose which one of those two becomes your domain. On the left, on your left too, it is the blue region. Blue region became the domain. On the right, it is green region. Green region is domain. Does make some sense? Yeah.
In this case, did we choose only one M for both?
No, I think it is different M for both of them, because you can see how perfectly they envelop each other. I probably handpicked M or did some algorithm or whatever. Yep. So it would be better to have like M1 and 2 here, etc. That would be better. But it's a lot of hassle to do it. But your solver will be thankful. More questions? Yes.
It's still not clear for me how we get the third, the biggest one polytope.
Come again?
How we get the biggest polytope on the pictures?
How we get relaxed polytope? Yeah. Do you understand how we get a blue and green polytopes? How did we get them?
We know them.
I mean, they are given us this representation. I know only A and B. How did they get the polytopes? I mean, I just know inequalities. How did I draw the polytopes? Well, here's the answer. I converted inequality into V representation, into vertex representation using vertex enumeration algorithm. Basically, I called conv2vert in MATLAB. Right? Or, equivalent. You can do equivalent in Python. It doesn't matter. And by the way, it's not a MATLAB function. It is a function written by some other guy. Okay. And that's how I get points. And then I draw them using patch. Basically, a tool to draw polygons using vertices. That's how I draw the green figure and blue figure. That's clear now, okay? Now, how did I get a big polygon? Well, I called, vertex enumeration for this guy. Just added M to it and called vertex enumeration again.
So by simpler words, we just multiply our polytopes by M.
Come again?
We just multiply our known polytopes, the smallest one, by M.
No, we did not. Let me state again. The original polytopes were we got them by calling vertex enumeration AX less than or equal to B. So AB is input parameters to vertex enumeration. Output are vertices. We plotted them on the graph. I emphasize the fact that we are talking about how I got the picture. I'm not talking about how we got the polytope. I'm talking about how I got the picture, because that's what your question is. And we'll come back to it in a second. Now, how did I get the picture for a big one? Well, I code A and as a first parameter, and B plus M times 1 as a second parameter. And I got new set of vertices. And I plotted a patch for those vertices. And that's how I got the big one. Now, why did I emphasize pictures? Well, because what you ask is how we got the polygons, but or polytopes. But the thing is, this is a polytope. Like this is a polytope. You don't need to get it. It's already there. And this is again already a polytope. We don't need to get it. It's a polytope. We cannot plot it graphically very easily. To plot it graphically, we would like to have vertex enumeration done. Then it is very easy to plot them. But that's the question about how to create a good graphics. It's not a question about geometry. Geometry is all there. This is a polytope. You don't need to convert it into anything. Like this is a small one, this is a big one. So, and that's important to recognize. It's like you ask yourself a question and you think, okay, what exactly do I want? And you recognize, okay, I'm talking about how to plot them. Because it's like geometry is already here. It's encapsulated in H representation already. So, but it's a good question. It comes to the heart of polytopic, thinking about polytopes, right? Difference between representations. Cool. More questions. No. Okay. Yes.
Can you name a real-world physical phenomena that this mathematical relationship represent?
Come again at the beginning of your question. I didn't catch it.
If you can name a real-world physical phenomena that this mathematical relationship represents.
This mathematical relationship, I don't want to be too philosophical here, but it doesn't represent any physical phenomena. In fact, I would say that mathematics doesn't in general. So it's not like, when we talk about like Newton laws and classical mechanics, we sometimes tend to use analogies from real world. We would say, okay, this represents gravity, this represents something else. But that is, that is more of a motivational thing anyway. So no, this doesn't represent anything from real world, and the concept itself is subject to, questioning that you need to do. So maybe you can reformulate your question in some other terms, and I can answer it. I expect you want me to give you like examples or whatever.
So just in case if you got anything in your mind just to represent this Bic-M method in real world, I'm thinking about that just to handle it in my mind.
Well, if you want, do you want examples of how to use Bic-M, where Bic-M is used?
Yes, of course.
Yeah, path planning. Path planning, the examples that we are doing currently.
Okay, thank you.
There are numerous ones. Hybrid system control, where you want to choose one of the two possible dynamics. Trajectory planning for a quadrator that you want to go, path to the left of the pillar or to the right of the pillar. Parking for a car, where a road is one polytope, parking space is a different polytope, parallel parking. Before we talked about economy, purchasing problems, where you can purchase some of the things in quantities expressed by real numbers, like kilograms, and something else in quantities by how many, like 2, 3, 4, like robots, for example. Together they form a mixed integer problem, and if you have constraints that have to be satisfied, that's a mixed integer problem. Okay, let's say you have your economic setting, examples that you need to satisfy one of two constraints. either you have to produce it on the factory A or on the factory B. And both factories have its own set of inequalities, like input constraints, output constraints, etc. And you have to choose which one to use. You have to use Bic-M, etc. Is that good?
Yes, thank you. Thank you very much.
No, sorry I didn't understand your question first. Cool. No more questions? Or? Okay, let's move on. One last thing that I want to show you. You don't have to write this problem for one variable. You can write it for like k variables, okay? And all you do is you write x1, x2, xk here, and make sure it holds for all of those k variables. By the way, maybe you can ask me instead of, yes, you can ask me. I will answer your questions directly. It will be more beneficial for the class. All right, so difference between expression 6 and expression 5 is only that x is not one variable, but a collection of variables. All the same as the rest, right? So, you know, that's just a minor point. Okay, good. Now we are set up to solve our trajectory, footstep planning. So here is a footstep planning with Bic-M relaxation. No, notice cost is the same. We write our, our footsteps to be inside the A-B polygon, which is relaxed with Bic-M. And we say that for each footstep, notice subscript k here, we'll have a separate set of C variables, C1, C12, C13, C14 for x1. For x2, it will be C12, C22, C32, etc. So those variables are one variable for each polygon. Inside each polygon, one variable for each x. Or if you want, one variable for each x, and for each x, as many variables as there are polygons. Okay, and that is it. Looks very compact, and it is compact. You do 2 cycles in your CVX program, and that's it.
The key here is 2, right?
Hmm?
The key here is 2.
K here is n. Oh, sorry, k. K is like whatever.
I mean, our problem was 2.
In our problem, no. The number of steps would be like, let's say 20. Yeah, for example, 20 steps, let's say, or 14 in the example on the blackboard. So k is any integer number. It's not a variable here, it's just index. Okay, n here is a number of is a number of polygons. Okay. One more thing. You can remember your suggestion. You said steps should be only like ½ meter long. Well, what you can do is actually punish the footsteps for being too long. You can say if footstep is a little bit too long, or just too long, you add a cost on it. This cost that I try to highlight is exactly that. You would say, okay, we'll add a omega times norm of each footstep, length of each footstep, to the cost function. Is it going to be, you could square it. If you square it, it's definitely going to be even, right? It's with a norm, I'm not sure if it's going to work perfectly well. I think it would. What would it prevent? It would prevent from footsteps doing something like this. Instead, they will be like this. Okay, that will be prevented. But it's not going to, I think, prevent something like this. because it's the same. Sum of norms is going to be the same. So instead, this is not going to happen, but you can have one footstep and then many short ones. So if you want to prevent it, what you can do is square the norm. Then if you square the norms, this type of footsteps is going to be preferred to this type of footsteps. Why? Because the square of this norm is going to dominate all of the squares here. So if you want to even out distances, always square them in the cost function. If you want to have y equal to x1 plus x2 plus x3, and you want x1, x2, x3 approximately equal, make square of them in the cost function. It's always going to be, the solution is always going to be approximately even distances. That is how norms work, squares of the norms. Okay, that's footstep planning. That is a realistic footstep planning. What you don't have here, so this is beyond the lecture. So I just give you, since you are robotics students, let me just give you pieces of information from the field. So first of all, you planned for a point. You can plan for the whole foot. That if foot is convex, just plan for the edges or vertices. Sorry. If vertices are all inside your region, the whole foot is inside your region. So that's it. Foot can rotate. That is not convex. You cannot do it as a convex optimization, but you can still do it as a mixed integer optimization. Basically, you represent your sines and cosines as piecewise linear. And those pieces, you represent choice of the piece is represented by mixed integer variable. That is the Drake and Dates, I believe. I hope I'm not mixing anything. Paper, mixed integer footstep planning for Atlas robot. I mean, I don't remember the whole title, but you'll find they presented this formulation. Okay, what else? This is for even terrain. For non-even terrain, you can do like height maps and turn them into like two-dimensional representation. But in general, it is a three-dimensional representation. And then domain can become non-convex very easily. So be careful about that. Typical footstep planners often work with non-convex domains. But what they can do is, for example, they plan the position of the footstep and then they orient the foot to accommodate the orientation of the surface, right? So you have a foot, you know it's supposed to be like this, but your terrain is like this, so you put it like this. Okay, that's very easy. It's post-processing basically, not a part of the solution. Orientation is much more difficult. Orientation is important, by the way. If you notice, let's say I'm trying to go from here to here. My feet are now oriented like this. Now they are oriented differently. And I cannot change the orientation of the feet instantaneously. And more than that, if I orient my feet differently, my whole leg is going to orient differently. So there can be kinematic constraints there. Like some robots cannot orient their feet very easily. All right, so orientation of the feet is a big problem. Position of the feet, mixed integer, convex optimization. But as I said, you can do orientation as a mixed integer as well. So good. Let me now show you any questions before we go to the code. Okay, here's the code for footstep planning. So first, you define shifts. What do you mean by shift? Basically, all of this section of the code is just to define 3 regions where you want your planner to be. 3 regions, okay? Now, all of this is just to turn them into a V representation. It's completely unnecessary, by the way. It just helps for printing. And this is your A and B, H representation of your regions. So the first page is just a problem statement. Second page, number of steps. 7, starting point, finish point, weights, and Bic-M is 15 in this case. Okay, now this is CVX, so we write CVX begin. Create X as the n by number of steps variable, n is equal to 2. Binary variable C, same as before. We add cost on the step size. We add cost on the starting and final point. That's it. We designed our cost. Now constraints. Constraints are, as I said, you recognize it's just literally the same as we saw before. And notice this one. And then I plot the solution. That's it. That's all program. Yes.
Previously in the formula, there was a constraint about the key.
About what?
About the key.
K?
Yeah.
Let's go look here. Last one? It's not a constraint. That is the statement about which indices we have. K is not a decision variable. How do you recognize it? Yeah, by the way, here there is a mess. Decision variables should also include C here. K is not a decision variable, it's just the index. So, all right, more questions? I'm not sure if we have a picture. No, we don't have a picture, it's too bad. But basically this code will just print you like your footsteps. Too bad I didn't put a picture here, I should have. But anyway, that's pretty much it. I think this code might be on the GitHub, might be, I don't know. And you can run it there. Now, those of you who took your projects in, let's say, cars, drones, or quadrupeds, or bipeds, or whatever, consider using this. Parallel parking, you almost definitely need mixed integers there to do it. Trajectory planning for a drone, almost definitely need mixed integers there to do it. No, like anything that where bulky body has to move through space, and the space is not non-convex, you need a mixed integer. So consider it. Also, remember what I said in the beginning. That is, this program is, key to the state of the art. One way we employed it recently is what we did is we had an integrity structure with a number of nodes. We say each node has to be connected to only one node via a rod, so a compressive body, and to at least 3 nodes via a cable, so tensile body. And this is a mixed integer program. We also wrote a conditions for it to be, what do you call it, for it to be statically stable. There is a force density method, not going to go into it, but basically it is a linear constraint. And with that, we wrote a generation as a mixed integer. That's, by the way, not our invention. We added to it ways to prioritize certain types of sparsity patterns, etc. The generation. You can find our paper. But that was done by, the coding was done initially by me, but then the rest by master student. Exactly your peer. Like, right now you are his peers. Like he knew about it exactly as much as you do. So you have now tools to do this type of research. And hope this feels empowering. Consider trying it for your project. And if your project doesn't fit it, consider just trying it on your own. It's very, very, very useful. And if you're interested in doing something like this for research outside of whatever you are doing currently, we can talk. I think this is extremely important and good, but up to you what you want to do it with it. Yesterday, Monday's lecture by Oleg also included this thing. there was a choice, there was a hybrid system which hit a wall. You remember? The dynamics is described using Bic-M, because you have to use Bic-M to describe two dynamics which switch. Only one of them is active at the same time. So this is another example why it is useful. All right, that's it from me. This is the last core lecture. What I mean by core is the last one that I expect to see on exam. But at the same time, we still have a little bit of time. So maybe I'll bring a little bit more material next week, which would be beneficial for you. And again, close to the state of the art. And we can have a practical session if you want to. Let me know. Let me know if you need practice for particular anything. We can do coding, we can do Blackboard exercises, anything you want. Let me know in advance, okay?
Can we know the structure of the final exam?
The final exam will be, I will give you a problem. It will be written out. Each of you will have a different one. You'll solve it. Maybe like each of you have a different one is maybe, maybe two of you have the same one. We'll see, because now there are a whole lot of students, but I will try to make sure each of you have a unique one. So anyway, you definitely won't know if I give two of you the same problem, and trying to communicate is going to waste your time. So, and you'll solve it, and then you solve it as in like propose a solution. And we discuss. We'll have like 7 to 10 minutes to discuss. You try to demonstrate me your understanding of the subject in 7 or 10 minutes. That's your exam.
And what about the length of the exam?
Length of the exam?
Yeah, like 1 hour? Or...
No, I mean, you'll have a preparation time of 1 hour. Or maybe like 40 minutes, I will tell you, but 1 hour probably is too long, probably like 40 minutes. But basically that's for the first one who goes, because everyone else, the preparation time depends on how fast students go. But I will try to keep it to 7 minutes or like 10 maximum. That means that we'll go in batches. So first we'll have like, I don't know, let's say 7 students get their 7 is too many, right? 5 students get their tasks. When your time is up, I give next 5 students their tasks, and I talk with your first 5 students, and rotate like this. So hopefully it doesn't become too crazy, because there are quite a few of you, and it may take time to go through exam. Hopefully it doesn't become too long. So 2 years ago we did programming exercise. So since we still have a little bit of time, I might consider giving you programming exercise. It is much faster for me, but while it's faster for me, it can be a little bit scary for you. So like I think oral exam is kind of more accurate. Exam will be not theoretical. I will give you a problem. You have to solve it, but not without coding. Yeah, you have to outline a solution for me. What we saw throughout the course. Not the same. Definitely not like. You don't need anything that you haven't seen on the slides, but you might have to need everything that we have on the slides. So the problems are not going to be like same as in the examples, but they are going to be related to robotics also.
Can we get like some kind of like test problems that we can practice on?
Those slides have homework exercises. I would probably consider them as the good ones. They're not the same as in the exams, but they at least give you a way of thinking that I put into exam design. So
we just like need to go through the slide with the homeworks in the slide.
That would be helpful. Or you can also look at the examples that I give through the lectures. I mean, there are not a lot of them, but they are pretty similar to the exam tasks, the big examples that I give, like today, for example.
by solution, what do you mean? The exact numbers?
No. Outline of what kind of procedure, what kind of transformation you need, what is going to be QP, SCP, what kind of constraints you need to take into account, etc. So just outline. Sounds good? All right. Any more questions, guys who are online? Okay. Yep. Yep. Yeah, who are binary. Yep. All right. Thank you, everyone. And we'll see each other on Monday.
Professor.
Yeah. Was there a question?
Yes, it's not exactly a question, it's a request.
Yep.
Okay, could you please upload the previous lecture?
They are uploaded. I upload them. They are on the Git. Sorry, I didn't post the links to the chat. In the Git, now there are links to the new last lectures. One of them is not recorded, by the way. There was one lecture that we didn't record, remember? So, all right.
Thank you, sir.
No, thank you. We'll see each other on Monday.